Chapter 30, Part 1 of the Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Bryan Travis. The Progress of Invention in the 19th Century by Wright Byrn. Firearms and Explosives. Part 1. Strange as it may appear, the evolution of an enlightened civilization and the deadly use of firearms have developed in parallel lines. What relation there may be between the adoption of the teachings of Christ to men to love one another and the invention of increased facilities among men for killing one another is a problem for the philosopher. Is it because killing at long range is less brutal, or does the deterrent influence of this increased facility operate as a check, appealing to the fear of the individual? Or is the canon one of God's missionaries in working out the great law of the survival of the fittest? Whatever it may be, there does seem to be some relation of cause and effect between the two factors, and doubtless all three of the causes have exercised a contributory influence. In the olden days, the wage of battle was almost universally decided by the strength of brawn, and the higher qualities of mind were subservient. The advent of firearms has changed all this. It has made the weakest arm equal to the strongest when supported by the same or superior mental equipment, and this has made a great step toward the supremacy of the intellectual against the attack of the physically strong. In the 5th century, the great civilization of Rome fell under the ruthless attack of the northern barbarian. Could such a thing have been possible with the gates defended by Gatling guns, magazine rifles, and dynamite shells? On the contrary, we find today a handful of trained soldiers equipped with modern firearms putting to flight a horde of ignorant savages. The history of modern wars is filled with illustrations of the shifting of the contest among men from an issue of brute force to a contest of brains, and of the support rendered the latter by firearms. But is war really necessary, and may we not hope that it shall cease? We can only say that the ideal sentiment of beating the sword into the plowshare is as yet the dream of the optimist, for man has gone right along in perfecting the arts of war and raising the execution of firearms to such a deadly efficacy that the 19th century, in a paramount degree, has been conspicuously notable for its advances in this art. Invention after invention has followed in such rapid succession even in the last years of the 19th century, until war now assumes the conditions of suicide and annihilation. No coherent history of firearms and explosives is possible in any short review. The cannon, bombard or mortar, musket, pistol, and petard all belong to former centuries, and in one form or another extend back to the most ancient times. But they have grown in the 19th century into such accuracy and distance of range, into such rapidity of action, into such multiplied efficiency in repeating systems, into such energy of explosives, and such convenient embodiment and penetration of projectile, that these subjects must needs be considered in separate divisions. The cannon is the most ancient of all firearms, and, like gunpowder, is believed to have had its origin with the Chinese. In the 11th century, the vessels of the King of Tunis in the attack on Seville are said to have had on board iron pipes from which a thundering fire was discharged. Conde, in his History of the Moors in Spain, speaks of them as used in that country as early as 1118. Ferdinand, in 1309, took Gibraltar from the Moors by cannon, and in 1346 the English used them at the Battle of Crecy, and from that time on they became a common weapon of warfare. In the first cannon used, the balls were of stone, and some of them were of enormous size. The bronze cannon of Mohammed II, A.D. 1464, had a bore of 25 inches and threw a stone ball of 800 pounds. The Tsar Pushka, the great bronze gun of Moscow, cast in 1586, was even larger and had a bore 36 inches in diameter. Early in the history of the cannon, the breech loading feature was introduced. In figures 265 and 266 are shown illustrations from the 16th century. Figure 265 representing a muzzle loader, and figure 266 a breech loader. Passing through various stages of development, the cannon came down to the 19th century. It was known generally as ordnance or artillery, and specifically as cannon or heavy guns, mortars for throwing shell at a great elevation, and howitzers for field, mountain, or siege, in which latter are lighter and shorter than cannon, and designed to throw hollow projectiles with comparatively small charges. The feature of importance in the cannon which contributed most to its efficiency was the rifling of the bore with spiral grooves. This, by giving a rotating effect to the projectile, caused it to maintain a truer flight by taking advantage of the law of physics that a rotating body tends to preserve its plane of rotation. The rifling of the barrels of firearms is, however, a very ancient origin. The British patent to Rachipan, number 71 of 1635, is an early disclosure of this art. The patent was granted him for, quote, 14 years, if he lived so long, to draw or to shave barrels for pieces of all sorts straight, even, and smooth, and to make any crooked barrel perfectly straight with great ease, and to rifle cut out, or screw barrels as wide or as close or as deep or as shallow as shall be required, with great ease. End quote. The rifle grooves, however, were first made spiral or screwed by Coster of Birmingham about 1620, while straight grooves are said to have been in use as far back as 1498. In Berlin, there is a rifled cannon of 1664 with 13 grooves. Rifled cannon were first employed in actual service in Louis Napoleon's Italian campaign of 1859 and were first introduced in the United States service by General James in 1861. About the middle of the 19th century, a great impetus was given to the development of artillery by the Crimean War, followed by the Civil War of the United States. In England, the Armstrong gun was introduced about 1855 and was covered by British patents number 401 of 1857, number 2564 of 1858, number 611 of 1859, and number 743 of 1861. This originally consisted of an internal tube of wrought iron or gunmetal with cylindrical casings of wrought iron shrunk on. It was afterwards improved in what was known as the Frazier gun. In Germany, the operations of Krupp as a gunmaker began to be notable about this period. In the United States, Colonel Rodman devised a means of casting guns of large caliber by having a hollow core through which water was circulated to rapidly cool and harden the metal in the vicinity of the bore, and to relieve the unequal strain in cooling. He obtained patent number 5236, August 14, 1847, for the same. The Dahlgren gun was patented August 6, 1861, numbers 32,983, 32,984, and 32,985 by Admiral Dahlgren, USN. The improvement covered the adjustment of the thickness of the metal at the breech of the gun to the varying pressure strains along the bore. These guns were distinguishable by the smooth, bulbous breech of great thickness and curvilinear contour. The Parrott gun, patented October 1, 1861, number 33,401, and May 6, 1862, number 35,171, comprehended a form of hooped ordnance in which the breech was reinforced by an encompassing hoop or sleeve, which was shrunk on. Breech loading ordnance. While the breech loading cannon is several centuries old, and was, in fact, one of the first forms of that firearm, it is to this principle of action that the rapid fire and great execution of the modern weapon are chiefly due. The earliest of existing forms of breech mechanism is that which comprehends the channeling of the breech transversely to receive a tapered plug, which permits the charge to be placed in the open rear end of the gun in front of the channel, and the transverse plug then closed behind the charge. This is described in Hadley's British patent number 577 of 1741, was first patented in the United States in a modified form by Wright and Gould, number 22,325, December 14, 1858, and afterwards came to be known as the Broadwell system, being developed by him and covered in patents number 33,876 of December 10, 1861, number 43,553, July 12, 1864, and number 55,762, June 19, 1866. This general principle is still employed by Krupp in some of his guns, and is used by him, as shown in Figure 267. The transverse channel through the breech is tapered, and the sliding breech block X is slightly wedge-shaped to fit tightly therein. When the breech block is withdrawn for loading, as shown, a sleeve S, shown in dotted lines, is temporarily arranged in alignment with the bore and gives smooth passageway to the charge to a position in front of the breech block. This sleeve is then withdrawn, the breech block forced in, and is there locked by a turn of the threads of a locking screw B into the corresponding recesses A in the breech. A detachable wrench E may be applied either to the screw DB to turn it to lock or unlock, or to the traversing screw C, which, by engaging with a nut not shown, runs the breech block in and out. By far the most popular principle of the breech block, however, is that of the interrupted thread, shown in Figure 268, in which the plug, when closed, has its axis in alignment with the axial bore of the gun. Its threads are interrupted by longitudinally arranged channels, and the breech of the gun has corresponding threads and channels. When the plug is pushed into the gun, the screw threads of the plug enter the channels of the breech, and a rotary turn of the screw plug then locks its threads into those of the breech. The screw plug is supported by a carrier hinged at one side to the gun and arranged to swing the plug into axial alignment with the bore, or be thrown to one side to admit the charge. The patents to Chambers, number 6612, July 31, 1849, reissue number 237, April 19, 1853, and to Cochrane, number 26256, November 29, 1859, are the earliest American examples of this principle of action, and are believed to be the original inventions of the same. In one form or another, this construction enters into most all modern breech mechanisms. Among the forms used by the United States are the Driggs-Seabury, the Dashiell, and the Vickers Maxim. To prevent the expanding gases from driving through the crevices of the breech block, expanding or swelling rings, known as gas checks, are arranged on the front of the breech block. Debonge's patent, number 301,220, July 1, 1884, covers the most popular form. The elements of efficiency of the modern rapid-fire breech-loading rifle are to be found in the following features. First, in the increased length of the gun, which for a 6-inch gun is now as much as 25 feet, the increased length lending a longer period of expansion for the explosion of the powder charge, and imparting a correspondingly higher momentum. Secondly, in the fixed ammunition, which means a cartridge case in which a metallic shell encloses the powder charge and is connected with the projectile. And third, in the great improvement in rapidity of action of the breech mechanism, which permits as many as 8 rounds per minute to be fired. In Figure 269 is shown a 6-inch rapid-fire gun of the United States Navy, loaded and being sighted for fire. Rapid-fire guns of this class represent the most effective form of modern ordnance. It was largely such rapid-fire batteries of Admiral Dewey's squadron that swept the Spanish fleet out of existence at Manila, and that demolished the fleet of Cervera at Santiago by the awful hail of shells poured into his ships. These relatively small guns throw a shell 6 miles, and the striking energy of their projectiles at the muzzle is equal to the penetration of iron plate 21 inches thick, or 16 inches of steel. When the gun is loaded, it is held in the forward position by coil springs, enclosed in cylinders and holding a recoil seat for the trunnions, and also has two pistons traveling in cylinders filled with glycerin. When the gun is fired, the recoil causes it to slide back, carrying the pistons, and the recoil is checked by the resistance of the glycerin traveling through an opening past the pistons. After full recoil, the gun is automatically returned to its forward position by the action of the coil springs, which are compressed during the recoil. The gun crew is protected by Harvey-ized steel plate 4 inches thick, and the gun is so delicately mounted on ball bearings that its great weight of 7.5 tons responds readily to the slight pressure in training the same. Powerful as these guns appear to be, their big brothers in the revolving turrets are far more so. While not so nimble in action, the great power of these guns of the main battery and the elaboration and completeness of mechanism for operating them, for supplying them with ammunition, and for rotating the turrets constitute a complete world and ordnance in itself. As the gun increases in size, its cost, both in construction and service, increases in a greatly disproportionate ratio. A 6-inch breech-loading rifle costs $64.40 for each discharge, while a 12-inch gun costs $458 for each discharge. The largest guns of our battleships are of 13-inch caliber and about 40 feet long, but larger ones are employed for seacoast defenses. The great 16-inch 126-ton gun, now building for the United States at the Watervliet Arsenal, is 49.25 feet long, over 6 feet in diameter at the breech, and it will have an extreme range of over 20 miles. Its projectile will weigh 2,370 pounds, and it will cost $865 to fire the gun once. The accompanying view, figure 270, will give graphic illustration of the range of this gun. If fired at its maximum elevation from the battery at the south end of New York in a northerly direction, its projectile would pass over the city of New York, over Grant's Tomb, Spuyten Duyvil, Riverdale, Mount St. Vincent, Ludlow, Yonkers, and would land near Hastings on the Hudson, nearly 20 miles away, as shown in our map, figure 271. The extreme height of its trajectory would be 30,516 feet, or nearly 6 miles. This means that if Pike's Peak of the Western Hemisphere had piled on top of it Mont Blanc of the Eastern Hemisphere, this gun would hurl its enormous projectile so high above them both as to still leave space below its curve to build Washington's monument on top of Mont Blanc, as shown in figure 270. The disappearing gun. The importance of secreting the location of the battery and coast defenses, and the better protection of the gunners, have suggested a species of gun carriage which would permit the gun to be normally hidden behind and under the protection of the parapet, and be only temporarily elevated to a position above the parapet while firing. Various forms of this have been devised. General R.E. de Russy, Corps Engineers, USA, devised such a carriage in 1835. Moncrieff of England was one of the first to put in practice such a form of carriage. United States patents covering this invention were granted him as follows: number 83,873, November 10, 1868; number 115,502, May 30, 1871; and number 144,120, October 28, 1873. Its principle of operation was to utilize the force of the recoil as a power to raise the gun into firing position. The gun is fulcrumed in a lever frame provided with a counterpoise which more than balances the gun. When the gun is fired, the recoil raises the counterweight, and the gun descends and is locked in its lower position. When loaded and released, the counterpoise raises the gun again to firing position. Among later gun carriages of this type of American construction may be mentioned those devised by Spiller, Gordon, Howell, and others, but the one most generally known is the Buffington Crozier, covered by patents number 555,426, February 25, 1896, and number 613,252, November 1, 1898. This carriage, sustaining the 8 and 10-inch breech-loading rifles at Fort Wadsworth for the defense of New York Harbor, is shown in figures 272 and 273, figure 272 representing it in its lowered position, and figure 273 in its elevated position for firing. The trunnions of the gun rest in bearings at the upper ends of the pair of levers, which latter are fulcrum near the middle to horizontally sliding carriages connected to hydraulic cylinders that move backward as the gun recoils. These cylinders move over stationary pistons, which have orifices that allow the liquid to pass from one side of the piston to the other. As the gun recoils and the levers turn to the horizontal position, the forward ends of the levers are made to raise vertically an immense leaden counterweight weighing 32,000 pounds, which ordinarily overbalances the weight of the gun on the levers. This cylindrical counterweight is seen raised on the left of figure 272. In firing, the energy of the recoil is absorbed partly by raising the counterweight, and partly by the resistance of the hydraulic cylinders, and when the gun reaches its lowest position, it is caught and retained by pawls. After loading, the pawls are tripped, and the greater gravity of the counterweight raises the gun to firing position again. 10 shots from an 8-inch gun on this carriage have been fired in 12 minutes, 21 seconds. The machine gun. During the Civil War, a gun made its appearance which, although of small caliber, rivaled in its deadly effectiveness the wholesale slaughter of the cannon. It was a new type and was known as the machine gun, or battery gun, in which balls of comparatively small size were discharged uninterruptedly and in incredible succession. It was the invention of Dr. R.J. Gatling, and was covered by him in patents number 36,836, November 4th, 1862, and number 47,631, May 9th, 1865, and in many subsequent patents for minor improvements, and is now universally known as the Gatling gun. It consisted of a circular series of barrels mounted on a central shaft and revolved by suitable gears and a hand crank. The cartridges were automatically and successively fed into the chambers of the barrel, and its several hammers were so arranged in connection with the barrels that the whole operation of loading, closing the breech, discharging, and expelling the empty cartridge cases was conducted while the barrels were kept in a continuous revolving movement by turning the hand crank. In figure 274 is shown a modern example of the Gatling gun, equipped with the Ackles feed. Ordinarily, the gun has 10 barrels with 10 corresponding locks, which revolve together during the working of the gun. When the gun is in action, there are always 5 cartridges going through the process of loading and 5 empty shells in different stages of being extracted, and many hundred shots a minute can be fired. Many modifications of this gun have been made by Hotchkiss and others. Maxim, Nordenfeldt, and Binet have each made valuable inventions in machine guns of a somewhat different type, some of which utilize the force of the exploding charges to react on the feed and firing mechanism, and thus furnish the power to continue the consecutive operation of the gun so that no hand crank is required, but the gun works itself with an incessant hail of balls until its supply of cartridges is exhausted. The dynamite gun. Most impressive to the layman, and most demoralizing to the enemy, is this latter-day form of ordnance. The first efforts to hurl dynamite shells from a gun were made with compressed air for fear of prematurely exploding the sensitive dynamite in the gun, which would be more disastrous to the gunners themselves than to the enemy. The Zelensky dynamite gun was of this class, and the first which attained any notoriety. Foolhardy as it might appear, Yankee genius was led to believe that dynamite shells could be fired with powder charges, and this is now done in a practical and safe way in the Sims-Dudley dynamite gun. This is manufactured under the fundamental patents of Dudley, numbers 407,474, 407,475, 407,476 of July 23, 1889, which cover a method of exploding a charge of powder in one gun barrel and causing it to compress the air in front of it, and force it into another barrel behind the dynamite shell so that this relatively cool body of air is interposed between the hot powder gases and the dynamite. Figure 275 represents Dudley's patent drawing. C is the powder charge in barrel A, and H is the dynamite shell in barrel G. The front of barrel A is connected to the rear of barrel G behind the dynamite shell by the tube F. When the powder C explodes, all the air in barrel A and tube F is driven out and acts on the dynamite shell H to discharge it without allowing it to come in contact with the hot powder gases. A frangible plate D closes the end of barrel A, but blows out above a certain pressure to avoid bursting strain in the gun. The Sims patent, number 619,025, February 7, 1899, covers a more simple and practical form of constructing a gun on this principle, and the gun as used in the United States is constructed in accordance with this latter improvement. End of Chapter 30, Part 1. Chapter 30, Part 2 of the Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Bryan Travis. The Progress of Invention in the 19th Century by Edward Wright Byrn. Firearms and Explosives, Part 2. Small arms. Pistols and guns are the two classes into which the layman divides small arms, although in latter years this classification has been much disturbed by the Western frontiersman, who calls his pistol a gun, and by the artillerist, who also calls his cannon a gun. The pistol may be defined as a small arm held in one hand to be fired. It is an ancient weapon, but had attained no special importance or popularity prior to the 19th century. The dueling pistol, with its long barrel, its hair trigger and inlaid stock, and the derringer, with its short barrel of large bore, were the popular forms. Not until the revolver made its appearance did the pistol attain any importance. Colt is popularly credited with having invented this, but it is really a very old principle. In the Alte Deutsche Drehung der Rückladungsgaswiller by Edward Zernin, 1872, Darmstadt and Leipzig is shown an ancient form of matchlock revolver, said to belong to the period 1480 to 1500. It is probably the same as the matchlock revolver in the Museum of the Tower of London, which is also credited to the 15th century. In the British patent to Puckle, number 418 of 1718, is shown and described a well-constructed revolver carried on a tripod, and of the dimensions of the modern machine gun. The inventor naively states that it has round chambers for round balls designed for Christians, and square chambers with square balls for the Turks. The first revolving firearm in the United States was made by John Gill of New Bern, North Carolina, in 1829. It had 14 chambers and was a percussion gun, but was never patented. The first revolver patented in the United States was that to D.G. Coburn, June 29, 1833. The revolver of Colonel Samuel Colt was patented February 25, 1836, reissue number 124, October 24, 1848, and again, August 29, 1839, number 1304, September 3, 1850, number 7613, and September 10, 1850, number 7629. It was the first practical invention of this kind, and it embodied as a leading feature the automatic rotation of the cylinder and cocking by a pawl on the hammer engaging a ratchet on the end of the cylinder. Various types followed, such as the Ode pepper box, patented by Darling, April 13, 1836, the self-cocking pepper box, patented by Allen, number 3998, April 16, 1845, the 4 sliding barrels of Sharp, number 6960, December 18, 1849, and many others. The most popular and successful, however, of the succeeding types is that of Smith and Wesson, shown in Figure 276, and covered by many patents. One of its most important features is the simultaneous extraction of the shells by an ejector, having a stem sliding through the cylinder. This was the invention of W.C. Dodge, patented January 17, 1865, number 45912, reissue number 4483, July 25, 1871. In Figure 277 is shown Smith & Wesson's latest pattern of hammerless safety revolver, with automatic shell extractor and rebounding lock. The latest development in this class of arms is the automatic magazine pistol, designed for the use of the officers of the German army and adapted to fire 10 shots in as many seconds. Only a slight pressure on the trigger is necessary, as it is not required to perform the work of turning any other part by the trigger, as is the case in the self-cocking revolver. The pressure of gas at each explosion does all the work of pushing back the closing piece of the breech through the recoil of the shell, extracts and ejects the shell, cocks the hammer, and also compresses recuperative springs, which effect the reloading and closing of the weapon. All of these functions being performed in proper sequence at each explosion in a fraction of a second. The act of firing thus prepares the pistol for the next shot automatically. In Figure 278 are shown 2 makes of pistol of this type. Number 1 is known as the Mauser, United States Patent number 584,479, June 15, 1897. Number 2 shows it with an extemporized stock, to be used as a carbine in firing from the shoulder. This stock is hollow and forms the holster or case for the pistol. At number 3 is shown the Mannlicher pistol, United States Patent number 581,296, April 27, 1897, which is another form of the same type. In the Mauser, the breech moves to the rear during recoil. In the Mannlicher, the barrel moves to the front, leaving space for a fresh cartridge to come up from the magazine below. The caliber of this pistol is 3/10 of an inch, and the initial velocity 1,395 feet. At 33 feet, the ball passes through 10 3/4 inches of spruce, at 490 through 5 inches, and its extreme range is 3,000 feet, or more than half a mile. When empty, it is quickly recharged with cartridges, which are made up in sets of 10 in a case and inserted in one movement. Breech-loading guns. Although the breech-loading principle was well known prior to the 19th century, it remained for this period to give it effective development. The first United States patent for a breech-loading gun was to Thornton and Hall, May 21, 1811. It was a flintlock, and many of these arms were made at Harper's Ferry Armory in 1814 and issued to the troops, one being given by order of Congress to each member of Congress to take home with him to show to his constituents. The present style of breakdown gun was invented by Poly in France and is to be found in his British patent number 3833 of 1814. La Faucheux of Paris, however, made this form of gun practical. Meinsinger, in United States Patent number 6139, February 27, 1849, supplied the important improvement of making the front edge of the metallic cartridge shell thinner than elsewhere, so as to expand by the pressure of the exploding charge and swell to a tight fit of the barrel. The Maynard rifle, first patented May 27, 1851, number 8126, was one of the earliest practical forms of breech loaders. Magazine guns. Walter Hunt's United States Patent number 6663, August 21, 1849, was the first on a magazine firearm of modern type. It had a sliding breech block carrying the mainspring and firing pin. The Spencer rifle was one of the early ones that came into use. This had a row of cartridges in the stock and was first patented March 6, 1860, number 27,393. It was this weapon which in the Civil War gave proof of the deadly efficacy of the breech-loading magazine gun and its superiority to the old-style military arm. Another type of magazine firearm which in the last half-century has gained great prominence and popularity is the so-called Winchester. This has its cartridges arranged in a tube below and parallel with the barrel, and they are fed in a column to the rear by a helical spring as fast as they are used up at the breech. The pioneer of this type is the arm patented by Smith & Wesson, February 14, 1854, number 10,535, reissued December 30, 1873, number 5,710. This was subsequently improved as to the extractor by B.F. Henry in patent number 30,446, October 16, 1860, reissued December 7, 1868, number 3,227, and was manufactured and favorably known for many years as the Henry rifle. This rifle was also used in the Civil War. O.F. Winchester subsequently reorganized it in patent number 57,808, September 4, 1866, and the arm in late years has taken his name. The needle gun of Prussia represents an early form of breech loader and may be considered the prototype of the modern bolt gun. The needle gun has in the place of the swinging hammer a rectilinearly sliding bolt carrying in front a needle which pierces the charge and ignites the fulminate by its friction. Its construction permits the fulminate to be placed in advance of the powder, which thus burns from the front and is entirely consumed in the gun, instead of being partially blown out of the gun, as may occur when ignited in the rear. The needle gun was invented by Dries in 1838 and was first introduced about 1846 and gave effective service in the Prusso-Austrian War of 1866. The chassepot, brought out in 1867, United States patent number 60,832, was a French development of the Prussian needle gun. About 1879, two forms of magazine guns appeared which have become types for most all subsequent guns of this class. Both of them employed the bolt system as previously embodied in the needle gun, but added to it the magazine principle and changed the method of supplying and feeding the cartridges. One was the invention of James Lee, and the other was the joint invention of Colonel Livermore of the Corps of Engineers and Major Russell of the Ordnance Department, USA. In the Lee, whose name has been much in evidence in late years, there was a relatively small detachable box, see Figure 279, capable of holding 5 cartridges and designed to be filled and then placed in a slot opening centrally under the gun, below the receiver, and directly in front of the trigger guard. A spring within the magazine fed the cartridges up into alignment with the barrel. Lee's first patent was number 221,328, November 4, 1879. The Livermore-Russell gun, patented October 28, 1879, number 221,079, had a magazine opening transversely in the upper edge of the stock behind the bolt, and the cartridges were fed to the barrel beneath the bolt. The important feature of the gun, however, was a cartridge case slotted on its side and detachable from the gun, and each bearing a group of 5 cartridges, which were to be thus made up in small packets and carried in the belt or cartridge box of the soldier. This idea was subsequently developed by Livermore and Russell in patent number 230,823, August 3, 1880, and this feature, viewed in the light of the importance subsequently attained by the clip in the Mauser and Mannlicher guns, may be fairly considered the pioneer of this idea of grouping cartridges in made-up packets for bolt guns. Its great advantage is the large number of shots that may be fired in a short space of time without an excessive weight in the gun itself. Subsequent patents for improvements were taken by Lee as follows: number 513,647, January 30th, 1894, and number 547,583, October 8th, 1895, and the gun used by the United States Navy is modeled along the lines of Lee's invention. The Krag-Jorgensen magazine rifle was patented June 10, 1890, number 429,811, and February 21, 1893, number 492,212. It is the arm adopted by the United States Infantry Service and is seen in Figure 280. The fixed magazine chamber, shown in the cross-section, passes through the breech laterally below the barrel and is filled with cartridges on one side of the gun, which cartridges pass through the breech laterally and, turning a curve, enter the barrel from the opposite side. When the bolt is drawn back by the knob handle, a cartridge is fed up into position to enter the barrel, and when pushed forward, the cartridge is forced into the bore of the gun, and at the same time, a spiral spring is put under tension to set the hammer of the gun, which carries a firing pin at its front end. When the trigger is pulled, the hammer and firing pin plunge forward to explode the cap in the cartridge, and when the handle of the bolt is drawn back again to extract the empty shell, a fresh cartridge rises to take its place. The Mauser rifle is shown in Figure 281. This is the arm of which so much was heard during the recent war with Spain, and against which our soldiers had to contend. 5 cartridges are carried in a magazine immediately in front of the trigger and are fed up by a sub-adjacent spring, one at a time, centrally through the breech, into line with the barrel, as the bolt with the knobbed handle is worked back and forth. The cartridges are carried by the soldier in groups of 5 in a clip, which is a simple strip of metal with in-turn parallel edges which enclose the flanged heads of the cartridges as they project at right angles to the clip. To transfer the cartridges to the magazine, the clip with its cartridges is placed above the barrel, and the cartridges forced down out of the clip into the magazine. In the Mannlicher gun, adopted by the German Army, the clip which holds the cartridges is itself inserted into the magazine along with the cartridges. The modern trend of development in firearms has been toward the reduction of caliber, the standard for small arms being 30. The lead bullets are covered with the seamless jacket of harder metal. Geiger's patents, number 306,738 and 306,739, October 21st, 1884, which prevents the leading and fouling of the gun and the distortion of the bullet. Modern magazine guns permit 25 to 30 shots a minute as single loaders, and besides they hold in reserve 5 cartridges. They have a killing range of a mile, and the cost of the cartridge is 3.2 cents. At a trial at the Washington Navy Yard a few years past, a steel projectile 1.07 inches long and .32 caliber penetrated solid iron 1.15 inches thick, fired at an angle of 80 degrees. It also penetrated 50 inches of pine boards, and its range was estimated at 3 miles. Hammerless guns. Among improvements in shotguns, the so-called hammerless feature is a noteworthy departure. This hides the hammers in the breech and cocks them by the act of breaking down the gun. In Figure 282 is given a section and plan view of the Greener mechanism, which was patented July 6, 1880, number 229,604, and was one of the first guns of this kind put on the market. The hammers, A, are constructed as elbow levers. Their upper ends have each a round point adapted to strike through a small hole in the breech onto the cap of the cartridge. The lower front portions of the hammers are extended forward and curved inwardly toward each other, so that their inner ends nearly meet. C is a pendant hook jointed to the barrel, and when the latter is tilted, as shown in dotted lines, the hook acting upon the forwardly projecting arms of the hammers turns them backward to the cocked position, in which they are retained by the dogs B, engaging with their notches. As the hammers move back, the mainspring is compressed, and when the dog B is removed from the notch by pulling on the trigger, the hammers are released and the gun fired. The rebounding lock, now universally applied to shotguns, is another comparatively recent improvement. This promotes safety by causing the hammers to be normally and automatically held away from the firing pins. The first practical form of this lock was patented by Haller, July 26, 1870, number 105,799, in which a single spring serves to deliver the blow of the hammer and also withdraws the hammer from the firing pin. A marked tendency in shotguns in late years is toward a reduction in bore, many sportsmen now using a 28 gauge in preference to the old regulation 12. Nearly 5,000 patents have been granted in the United States for firearms, and about 2,400 for projectiles. The most important of the latter is the torpedo, of which the whitehead, or fish torpedo, which supplies its own means of propulsion, is the best known and most used. It was first brought out in 1866 by Whitehead at Fiume, a port of Hungary. The Gathman aerial torpedo, weighing 1,800 pounds and carrying 625 pounds of wet gun cotton, is designed to be fired from a gun 44 feet long and 18-inch bore, and is supposed to have a range of 10 miles. Tests are about to be made under special appropriation of Congress, and if its claim can be substantiated, it may become the most destructive engine of warfare known. Explosives. The invention of gunpowder is ascribed to the Chinese, and at a period so far back that its origin is buried in antiquity. It is believed to have been known since the time of Moses, something very like it being mentioned in the ancient Gentoo laws of India 1500 to 2000 BC. For many years, it was thought that Roger Bacon invented it in 1249, but it is now known that he was only a factor in its development. Most likely, the saltpeter of the plains of China came first in accidental contact with the charred embers of a prehistoric fire, and to the observant man, the oxygen-giving saltpeter furnished the charcoal with its means of energetic combustion for the first time. Gunpowder consists of about 75 parts of saltpeter, nitrate of potash, 15 of charcoal, and 10 of sulfur, in proportions varying somewhat with the use to which it is to be applied. In ordinary combustion, the air supplies the necessary oxygen. In gunpowder, the presence of the air is not necessary, as the saltpeter has imprisoned in its composition a large quantity of oxygen, which furnishes to the carbon and sulfur the means for its combustion, gasification, and enormous expansion. Originally, gunpowder was pulverulent, like that used in fireworks, and had but little propelling force. The making of it in grains, corned, is ascribed to Berthold Schwarz, a German monk about 1320, and this, by promoting the rapidity of its burning, added greatly to its effective force and gave a new impetus to firearms. In the early part of the 19th century, there were but few improvements in either the composition or manufacture of gunpowder. The introduction of the percussion cap, which exploded the charge by a blow in the place of the old flintlock, was, however, a notable advance. Alexander John Forsyth, a Scotch clergyman, was the first to apply a percussion or detonating compound as set forth in his British patent number 3032 of 1807. The embodiment of such compounds in the little copper caps was made about 1818 and has been claimed by various parties. Manton's British patent number 4285 of 1818 describes a thin copper tube filled with fulminate and struck sidewise by the hammer to explode it. Joshua Shaw took a United States patent on a percussion gun, June 19, 1822, and the copper percussion cap was said to have been introduced in the United States by him in 1842. The embodiment of the charge of powder and ball in brass and copper shells was done in France by Gale Cazola as early as 1826. Drawn metallic shells were made by Flaubert and Lou Faucheux in 1853 and Palmer in 1854. Drawn copper cartridges with center fire were introduced in the United States and patented by Smith & Wesson, August 8, 1854, number 11,496, and solid-headed shells by Hotchkiss, August 31, 1869, number 94,210. In 1846, a new and distinct development in explosives was made in the discovery of gun cotton by Schoenbein, and of nitroglycerin in 1847 by Sobrero. The former is made by the reaction of nitric acid aided by sulfuric acid on ordinary raw cotton, which, while changing the physical aspects of the cotton but little, gives to it a terrific explosive energy. Nitroglycerin is made in a somewhat similar way by treating glycerin with nitric and sulfuric acids. At first it found no practical applications except as a homeopathic medicine for headache, but about 1864 Nobel commenced its manufacture for explosive uses, and since that time nearly all the great blasting operations have been performed through its agency. Its most familiar form is dynamite or giant powder. Nobel's patent, number 78,317, May 26, 1868, which is simply nitroglycerin held in absorption by some inert granular solid, such as infusorial earth, and is thus rendered safer to handle and more convenient to use. A suggestive application of the terrible powder of these explosives is in submarine mines. The instantaneous and dastardly destruction of our battleship, the Maine, with 250 of her crew in Havana Harbor, February 15, 1898, by one of these agencies, is a harrowing illustration. Figure 283 represents one of these submarine mines carrying 250 pounds of dynamite, and figure 284 is an instantaneous photograph at the moment of explosion. White gunpowder, or wood powder, was invented by Captain Schultz of the Prussian Army. It is made by treating granulated wood with a mixture of nitric and sulfuric acids, which, acting upon the cellulose of the wood, convert it into an explosive, something of the nature of gun cotton. The grains are afterwards saturated with saltpeter. This was patented in the United States June 2, 1863, number 38,789, and in Great Britain number 900 of 1864. Dittmer's powder is another of the same general nature, covered by United States patents number 98,854, January 18, 1870, number 99,069, January 25, 1870, and number 145,403, December 9, 1873. Among the high explosives of more recent date may be mentioned tonite, gun cotton and barium nitrate, British patents number 3,612 of 1874 and number 2,742 of 1876. Raca-rock, potassium chlorate and nitrobenzene, United States patent number 243,432, June 28, 1881. British patent number 5,584 of 1881. Bellite, ammonium nitrate and nitrobenzene, United States patent number 455,217, June 30th, 1891. British patent number 13,690 of 1885. Melanite, picric acid and gun cotton, British patent number 15,089 of 1885. Lyddite, not patented, but believed to be substantially same as melanite, and containing for its active ingredient picric acid, which is a compound formed by the reaction of nitric acid on carbolic acid. Cordite, nitroglycerin, gun cotton, and mineral jelly or oil, British patent number 5,614 of 1889, United States patent number 409,549, August 20th, 1889. Indurite, gun cotton and nitrobenzene, indurated, United States patent number 489,684, January 10th, 1893, British patent number 580 of 1893. In recent years, smokeless powders have largely superseded all others. These contain usually nitrocellulose, gun cotton, or nitroglycerin, or both, made up into a plastic, coherent, and homogeneous compound of a gluey nature, and fashioned into horn-like sticks or rods by being forced under pressure through a die plate having small holes, through which the plastic material is strained into strings like macaroni, or else is molded into tablets, pellets, or grains of cubical shape. Prominent among those who have contributed to this art are the names of Turpin, Abel and Dewar, Nobel, Maxim, Monroe, DuPont, Bernardieu, and others. In the recent years of the 19th century, great activity has been manifest in this field of invention. In the United States, more than 600 different patents have been granted for explosives, the larger portion of them being for nitro compounds, which partake in a greater or less degree of the qualities of gun cotton or nitroglycerin. The influence exerted by them has been incalculable. Subtle as is the force imprisoned in interatomic relation, it has been the power behind the boom of the cannon. It has lent itself to the driving of great tunnels through the solid rock. It has lifted the coal and ore from the solid embrace of the mountain, and the building stone from its sleep in the quarry. It has opened up channels to the sea, canals on land, and in both war and peace has been one of the great agencies of civilization. End of Chapter 30, Part 2.
Chapter 33 of the Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Jennifer Beckett Wood. The Progress of Invention in the 19th Century by Edward Wright Byrn. Chapter 31. Textiles. Far back in the obscuring gloom of a prehistoric antiquity, man wore probably only the hirsute covering which nature gave him. As he emerged from barbarism, sentiments of modesty marked the evolution of his mind, and this, together with the need for a more sufficient protection against cold and heat, suggested an artificial covering for his body. At first he robbed the brute of his fleecy skin and wore it bodily. Later he learnt to spin and weave. Next to food and drink, clothing became a fundamental necessity, for without it his life could not extend outside of the limited zone of the tropics. Food and drink were to be found as nature's free gifts, but clothing had to be made, and its manufacture constituted probably the oldest of all the living arts. The making of cloth may be said to be coeval with history. The Old Testament of the Bible is replete with references to spinning and weaving, and the cloths wrapped about the mummies of ancient Egypt, although thousands of years old, were of exceeding regularity and fineness. So old an art, and so great and continuous a need for its products, necessarily must have resulted in much development and progress. When the 19th century began, the world already enjoyed the results of Hargreaves' spinning jenny, Arkwright's roll-drawing spinning machine, the mule spinner, the cotton gin, and the power loom, all of which were most radical inventions, equalling in importance, perhaps, any that have followed. Prior to the invention of the spinning jenny, the loose fibre was spun into yarns and thread by hand on the old-fashioned spinning wheel, each thread requiring the attention of one person. In 1763, Hargreaves invented the spinning jenny, see Figure 285, in which a multiplicity of spindles was employed, whereby one person could attend to the making of many threads simultaneously. For this purpose, the spindles were set upright at the end of the frame, and the rovings or strips of untwisted fibre were carried on bobbins on the inclined frame. The rovings extended from these bobbins to a reciprocating clasp held in the left hand of the workman, and thence extended to the spindles at the end of the frame. The workman drew out the rovings by moving the clasp back and forth, and at the same time turned the crank with his right hand to rotate the spindles. Hargreaves' machine is shown and described in his British patent, number 962 of 1770. The next important step in spinning was the introduction of drawing rolls, which were a series of rolls running at different speeds for drawing out or elongating the roving as it was spun into a thread. This was mainly due to Arkwright, a contemporary of Hargreaves. The principle of the drawing rolls had been foreshadowed in the British patents of Louis Paul, number 562 of 1738, and number 724 of 1758. But Arkwright made the first embodiment of it in practically useful machines, which were covered by him in British patents number 931 of 1769 and number 1111 of 1775. Arkwright's spinning machine is shown in figure 286, the drawing rolls being shown at the top of the figure. Following these important inventions came the mule spinner. This was invented by Crompton between 1774 and 1779, but was never patented. It combined the leading features of Hargreaves and Arkwright. The spindles were mounted on a wheeled carriage that travelled back and forth a considerable distance from the drawing rolls, which were mounted in bearings in a stationary frame. The long travel of the carriage back and forth, and the simultaneous twisting and drawing of the yarns, produced threads of great fineness and regularity. The value of the long travel of the carriage may be briefly noted as follows. When the threads or slivers emerge from the drawing rolls, they are not absolutely of uniform size, and the thick portions do not twist as tightly as the thinner portions. The stretching and drawing of these thicker parts down to a uniform size by the receding of the carriage is the distinctive feature of its action. As the thread has greater tensile strength at the thinner, hard-twisted parts than it has at the thicker, untwisted parts, it will be seen that the stretching action is localized on the thicker, untwisted parts of the thread, which are thus brought down to uniform size by elongation. The drawing and twisting of the thread is effected as the carriage runs out, and when the carriage runs in, these twisted lengths are wound around the spindles. The rendering of the action of the mule automatic or self-acting in its travel back and forth was the invention of Richard Roberts of England, and was covered by him in British patents number 5138 of 1825 and number 5649 of 1830. The mule spinner, shown in figure 287, is a good modern example of this machine. One of the most important of the early inventions in the textile art was the cotton gin. This was the invention of Eli Whitney of Massachusetts, and was patented by him March 14, 1794. Prior to its use, the picking of the cotton fibre from the bean-like seed with which it is compactly stored in the boll was entirely effected by hand, and it was a slow and tedious process, and about 4 pounds per day was the average work of one man. The cotton gin, shown in figure 288, is a device for doing this by machinery in a rapid, thorough, and expeditious manner. The cotton, mixed with seed, is fed to the roll box J, in which a sort of reel F continuously turns the cotton. The bottom of the roll box is formed with a grating of parallel ribs E, between which project the teeth of a gang of circular saws C, which pull the fibre through between the ribs and deliver it to the revolving brush B, which beats the fibre off the teeth of the saws and produces a blast that discharges the fleece through the rear of the gin. The cotton seed, which are too large to pass between the ribs with the fibre, drop out the bottom of the roll box. With the aid of the cotton gin, the efficiency of one man is raised from 4 pounds a day to several thousand pounds per day, and the culture and manufacture of cotton fibre was revolutionized and greatly stimulated by providing a mode of putting it into merchantable condition at a reasonable price. It is said that the crop of cotton increased from £189,316 in 1791 to £2,000 million in 1859. The cotton gin, as invented by Whitney more than 100 years ago, is still in use, substantially unchanged in principle, but its efficiency has been raised from £70 per day to several thousands. The cotton crop of the United States for 1899, which was handled by the modern gins at this rate, amounted to 11,274,840 bales, of about £500 each, or more than £5,000 million. But for the cotton gin, this great staple would have had only a very limited use, and one of the greatest of the world's industries would have had practically no existence. A modern step of importance in spinning was the ring frame. Ring spinning was invented by John Thorpe of Rhode Island, who took out 2 patents for the same November 20, 1828. The leading feature of the ring frame is the substitution of a light steel hoop or traveller running upon the upper edge of a ring surrounding the spindle, in lieu of the flyer formerly employed. The thread passes through the hoop as it is wound upon the spindle. In modern times, ring spinning has attained considerable proportions, especially in cotton manufactures. Nearly 3,000 United States patents have been granted in the class of spinning, and many valuable improvements in the details of construction in spinning machinery have been made in recent years. The most important, perhaps, are those relating to spindle structure, whereby the speed and efficiency of spinning machines have been greatly increased. Prior to 1878, the speed of the average spindle was limited to 5,000 revolutions a minute. In 1878, improvements were made which doubled its working speed and permitted as high as 20,000 revolutions a minute. This result was accomplished by making a yielding bolster. The bolster is an upright sleeve bearing in which the spindle revolves and against which is sustained the pull of the band that drives the spindle. By making this bolster or sleeve bearing to yield laterally by means of an elastic packing which surrounds it, a much greater freedom and speed of revolution were obtained. The preliminary step in this direction was made by Birkenhead in patent number 205,718, July 9, 1878. In the same year, this idea was perfected by Rabeth. The bolster was placed loosely in a bolster case of slightly larger diameter than the bolster, and the bottom of the spindle had a free lateral movement as well as the top, as shown in his patent number 227,129, May 4, 1880. With such perfect freedom of movement, the spindle at high speed could find its own centre of revolution, and an indefinitely high speed and quadrupled efficiency were attained. The Draper spindle is shown in figure 289 as one of the most modern and representative of spinning spindles. Considering the great speed of the modern spindle and the fact that a single workman attends 1,000 or more of them, the record of progress in this art becomes impressive. In 1805, there were only 4,500 cotton spindles at work in the United States. In 1899, there were 18,100,000. Weaving. A woven fabric consists of threads which run lengthwise, called the warp, crossed by threads running transversely, called the woof, weft, or filling, which latter are imprisoned or locked in by the warp. In a simple loom, the warp threads are divided into 2 groups, the threads of one group alternating with those of the other, and means are provided for separating these groups to form a wedge-shaped space between them, called a shed. Through this shed, the shuttle which carries the woof or filling thread is sent crosswise the warp threads. Means are provided for changing the inclination and position of the 2 groups of warp threads in relation to each other so as to lock in the filling and put the warp threads in position to receive the next filling thread. For this purpose, the warp threads, usually horizontal, are each passed through a loop, and every alternate loop is attached to a frame called a heddle. The intervening loops and threads are attached to another frame or heddle, and the 2 heddles, by being worked one up and the other down, separate the warp threads to form the shed. Formerly, the shuttle was thrown by hand through the shed. In 1733, John Kay of England took out British patent number 542 for the flying shuttle and picking stick, by which the shuttle was struck a hammer-like blow and driven like a ball from a bat across the warp, and was struck by a similar stick on the other side to be returned in the same way. This gave a much more rapid action than could be obtained by hand throwing, and enabled one weaver to do the work of 2 or 3. In 1760, Robert Kay invented the drop box, by which different shuttles carrying different colours of thread were employed. The power loom, however, marked the first great growth in the art of weaving. The enormously increased quantity of cotton spun by Arkwright's machinery made a demand for increased facilities for weaving it into cloth. Dr. Cartwright of England foresaw and met this demand in his power loom, in which all of the intricate operations were performed by power-driven machinery. His invention was not extensively introduced until about the beginning of the 19th century. One difficulty experienced was that the warp threads, from their fuzzy nature, had to be dressed with size, and this required the loom to be stopped from time to time, and necessitated the services of a man to dress or size the warp threads. This difficulty was overcome, however, by Johnson and Radcliffe about 1803, by the sizing and dressing of the yarns, by passing them between rollers and coating them with a thin layer of paste before being put into the loom. Dr. Cartwright was granted British Patents number 1470 of 1785, number 1565 of 1786, number 1616 of 1787, and number 1676 of 1788, but being unable to maintain any monopoly under his patents, he was compensated by Parliament with a grant of £10,000. Jacquard loom. This most notable step in the art of weaving was made at the very beginning of the 19th century. It enabled all kinds of fabrics, from the finest to the coarsest, to be cheaply woven into patterns having figured or ornamental designs. Jacquard, a native of Lyon, conceived the plan of his great invention in the last decade of the 18th century, and on December 28, 1801, took out French patent number 245 on the same. His invention was not, in fact, a new form of loom, but rather an attachment to a loom which was universally applicable to all looms. Before his invention, figured patterns of cloth could only be made by slow and laborious processes. Jacquard's invention consisted in individualizing and differentiating the movement of the warp threads instead of operating them in constant groups. This individualizing of the movement of the warp threads allowed any warp thread to be held up automatically any length of time or let down, according as was necessary to form the figure of the pattern. This was accomplished by making a chain of articulated cards, like a slatted belt, and perforating these cards with varying arrangements of holes. The cards were successively and intermittently fed to a set of needles, which latter, by rising and falling, raise or lower the warp threads attached to the same. By perforating these cards differently and arranging them so that when one card was brought in front of the needles, it would let certain needles through the perforations and hold the others back, it will be seen that each card controlled the action of a different set of needles, and the sequence of the series of cards effected the necessary change in the needles and movement of the warp threads to form the growth of the figure in the fabric. In figure 290 is seen a modern form of jacquard loom, showing at the far end the chain of perforated cards. Jacquard received a bronze medal at the French Exposition in 1801, was decorated with the Cross of the Legion of Honour, and the gratitude of his countrymen was attested by a pension of 6,000 francs and a statue erected to his memory at Lyon in 1840. Subsequent improvements and developments of the jacquard loom have carried its work to great nicety and refinement of action. In the chain of pattern cards, it is said that as many as 25,000 separately punched cards or plates are sometimes used in weaving a single yard of brocade. The great variety of elaborate designs of delicate tracery in silk, rich patterns in brocades, and gorgeous figures in carpets attest the value of jacquard's important step in this art. Nearly 5,000 United States patents have been granted in the class of weaving. In the early part of the century, much notable work was done. Steam was applied to looms by William Horrocks, British patent number 2699, 1803. From 1830 to 1842, there were brought out the fancy looms of Crompton, the application of the jacquard mechanism to the lace frame by Draper, and the carpet looms of Bigelow. In 1853, Bonelli sought to improve on the jacquard mechanism by employing electromagnets to effect the selections of the needles instead of perforated cards. British Patent number 1892 of 1853. Among the more recent developments is the positive motion loom of Lyell, patented December 10th, 1872, number 133,868, reissue number 9049, January 20, 1880. The distinguishing feature of this is that the shuttle is not thrown or impelled as a projectile through the wedge-shaped space, shed, between the two sets of warp threads, but is positively dragged back and forth through the same by an endless belt attached to the shuttle carriage and running first in one direction and then in the other to drag the shuttle through. It is not to be understood that the positive motion loom has superseded the flying shuttle. The latter is still the leading type, of which the Crompton fancy loom, shown in figure 291, is a representative illustration. The tendency in late years in the art of weaving has been toward labour-saving devices, a reduction in the cost to the consumer of all kinds of textile fabrics, and the extension of the loom to the weaving of new kinds of materials. Prominent among these are the inventions in the loom for weaving plain fabrics made between the years 1881 and 1895, shown in patents to Northrop, number 454,810, June 23, 1891, number 529,943, November 27, 1894, and Draper, number 536,948, April 2, 1895. This loom, as usual, employs a single shuttle, but as the weft becomes exhausted, another bobbin is automatically supplied to the shuttle without stopping the operation of the machine. During the year 1895, the first loom for weaving an open mesh cane fabric having diagonal strands was invented. Patents to Morris, number 549,930, and to Crompton, number 550,068, November 19, 1895, were obtained for this. Prior to this time, two distinct machines were necessary to produce this fabric, and the operation was slow and expensive. Between 1893 and 1895, two machines were invented, upon either of which the well-known Turkish carpets can be woven. Patents to Young John's, number 510,755, December 12, 1893, and to Reinhard von Seidlitz, number 533,330, January 29, 1895, disclose this. The drawing of warp threads into the eyes of the heddles and through the reed of a loom requires great skill, and prior to 1880 was performed by hand at great expense. In 1882, however, a machine for doing this was invented, thereby dispensing with the old hand method and cheapening the operation. Patents to Sherman and Ingersoll, number 255,038, March 14, 1882, and Ingersoll, number 461,613, October 20, 1891, were granted for this machine. Today, the shuttle flies at the rate of 180 to 250 strokes a minute, and yet the complex organization of the machine works with an energy, a uniformity, an accuracy, and a continuity that leaves far behind the strength of the arm, the memory of mind, and the accuracy of the human eye. And yet, if the tiny thread breaks, the whole organization instantly stops and patiently waits the remedial care of its watchful master. Knitting machines. Knitting differs from weaving, braiding, or plaiting in the following respects. In weaving, there are longitudinal threads called warp threads, which are crossed on a separate weft or filling thread. In braiding or plaiting, all the threads may be considered warp threads, since they are arranged to run longitudinally, and instead of locking around a separate transverse thread at right angles, they extend diagonally and are interwoven with each other. In netting and knitting, however, there is but a single thread, which, in netting, is knotted into itself at definite intervals to leave a mesh of definite size, while in knitting, the single thread is merely looped into itself without any definite mesh. Knitted goods have the peculiarity of great elasticity in consequence of this formation of the fabric, and for that reason find a special application in all garments which are required to snugly conform to irregular outlines, such as stockings for the feet, gloves for the hands, and underwear for the body. Weaving, braiding, and netting are very old arts, but the art of knitting is comparatively modern. It is believed to have originated about the year 1500 in Scotland. In 1589, William Lee of England is credited with making the first knitting machine. It is said that the girl with whom he was in love, and to whom he was paying his attention, was so busy with her work of hand knitting that she could not give him the requisite attention, and he invented the knitting machine that they might have more time to devote to their love affairs. Another version is that he married the girl and invented the machine to relieve her weary fingers from the work of the knitting needle. And still another is that the machine was the leading object of his affections, to the neglect of his sweetheart, who gave him the mitten before he had knitted one on his machines. The earliest circular knitting machine was by Brunel, described in British Patent number 3993 of 1816. Power was applied to the knitting frame by Bailey in 1831, and the latch needle was patented in the United States by Hibbert, January 9, 1849, number 6025. This patent was extended for 7 years from January 9, 1863, and covered a very important and universally used feature of the knitting machine. Research has shown, however, that the latch was not broadly new with Hibbert, as it appeared in the French patent to jenno, number 1900, of April 25, 1806. Among the earlier knitting machines, the straight reciprocating type was most in evidence, and of which the Lamb machine was a popular form. The increased speed and capacity of the circular machine have, however, caused it to largely supersede the others. In the circular machine, a circular series of vertical parallel needles slide in grooves in a cylinder and are raised and lowered successively by an external rotating cylinder, which has on the inner side cams that act upon the needles. The Branson 15/16 automatic knitter, shown in figure 292, is a good modern illustration. It performs automatically 15/16 of the various movements which ordinarily would be performed by hand on a hand machine. Its salient features are covered by patents number 333,102, December 29, 1885, and number 519,170, May 1, 1894. About 2,000 United States patents have been granted in the class of knitting and netting, and the value of hosiery and knit goods in the United States in 1890 was $67,241,013. An important branch of the textile art is cloth finishing, whereby the rough surface of the cloth as it comes from the loom is rendered soft and smooth. One method is to raise the nap of the cloth by pulling out the fibre by a multitude of fine points. Originally this was done by combing it with teasels, a sort of dried burr of vegetable growth, having a multitude of fine hook-shaped points. Machines with fine metal-card teeth are now largely used for this purpose, and of which the planetary napping machine of Ott, patent number 344,981, July 6, 1886, is an example. Another method of finishing the cloth is to iron or press it. Plate presses were first used, in which smooth plates were folded in alternate layers with the cloth and pressure then applied. But in later years, continuous rotary presses have been employed, that of Gessner, patent number 206,718, August 6, 1878, reissue number 9076, 9077, February 17, 1880, is one of the earliest examples of a continuous rotary press. The old Gessner presses of Saxony were the pioneers in this field. A modern Gessner cloth press is seen in figure 293. In the field of textiles there are many related arts and machines. There are hat felting and finishing machines, darning machines, quilting machines, embroidering machines, processes and apparatus for dyeing and sizing, machines for printing fabrics, machines for making rope and cord, machines for winding and working silk, and in treating the raw material there are cotton pickers, cotton baling presses, cotton openers and cleaners, flax breaks and hackling machines, feeding devices, wool carding and cleaning apparatus, all in variety and numbers that defy both comment and count. In fabrics, every class of fibre has been called into requisition. Flax, wool, silk and cotton have been supplemented with the fibres of metal, of glass, of coconut, pine needles, ramie, wood pulp, and of many other plants, leaves and grasses. Artificial silk is made out of a chemically prepared composition, and the fibres are spun by processes simulating not only the act of the silkworm, but its product in quality. Vandura silk was spun from an aqueous solution of gelatin by forcing it through a fine capillary tube, but it attained little or no practical value. A far more important artificial silk is covered by the patents to du Chardonnay, number 394,559, December 18, 1880, number 460,629, October 6, 1891, and number 531,158, December 18, 1884, and also in subsequent patents to Lehner and to Turk. These all relate to the manufacture of artificial silk by spinning threads or filaments from pyroxylene, solution of gun cotton, collodion, or some such glutinous solution which evaporates rapidly, leaving a tiny thread, having most of the characteristics of silk and produced by the same method employed by the silkworm when it expresses and draws out its viscid liquid. The de Chardonnay artificial silk took a Grand Prix at the Paris Exposition in 1889, and the industry is growing to considerable proportions. Large works are in operation at Besançon in France, producing £7,000 per week, and it is said that the plant is to be increased to a capacity of £2,000 a day. Similar works at Avon near Coventry, England, have an equal capacity, and other factories are about to be established in Belgium and Germany. Polished or diamond cotton is a lustrous-looking article of a soft, silky nature, formed by plating the threads with a liquid emulsion of a waxy and starchy substance and polishing the threads with rapidly revolving brushes. Mercerized cloth. In late years, a distinct novelty has appeared on the shelves of the dry goods stores. Beautiful filmy fabrics and lustrous embroidery thread, not of silk, but are so close to it in appearance as to be scarcely distinguishable, have gained much popularity and attained a large sale. They are known as mercerized goods. About the middle of the century, John Mercer of England found that when cotton goods were treated with chemicals, either alkalis or acids, a change was produced in the fibre which caused it to shrink and become thicker, and which imparted also an increased affinity for dyes. He took out British patent number 13,296 of 1850 for his invention, but practically nothing further was done with the process. Recently, the important step of Thomas and Prevost of mercerizing under tension gave some new and wonderful results. United States patents number 600,826 and number 600,827 of May 15, 1898, disclose this process. The cloth or thread, while being treated chemically, is at the same time subjected to a powerful tension that causes the fibres, softened and rendered glutinous by the chemicals, to be elongated or pulled out like fibres of molten glass, giving it the same striated texture and fine lustre that silk has. and by substantially the same mechanical agency, for it is the elongation of the plastic glutinous thread from the silkworm that gives the thread its silky luster, by a process which has a familiar illustration in the molecular adjustment that imparts luster to spun glass or drawn taffy. Standing in the light of the 20th century and looking back through past ages, we find the art of spinning and weaving in an ever-present and unbroken thread of evidence all along the path of history, through wars and famine, floods and conflagrations, through the progress and decay of nations, through all phases of change and the vicissitudes of centuries. It has never been relegated to the domain of the lost arts, but has remained a persisting invention. It has been a paramount necessity to the human race, indissolubly locked up with its continuity and welfare, and will ever continue to supply its work in maintaining the greater fabric of human existence. End of section 33.
Chapter 32 of The Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Verla Viera. The Progress of Invention in the 19th Century by Wright Byrn. Ice Machines. Very few people have any correct conception of the principles of ice making. Most persons have heard in a vague sort of way that chemicals are employed in its manufacture, and many a fastidious individual has been known to object to artificial ice on the ground that he could taste the chemicals, and that it could not therefore be wholesome. Such is the power of imagination, and such the misconception in the public mind. Nothing could be more erroneous, nor more amusing to the physicist, since no chemicals ever come in contact with either the water or the ice. An intelligent understanding of the operations of an ice machine involves only a correct appreciation of one of the physical laws governing the relation of heat to matter, and the forms which matter assumes under different degrees of heat. We see water passing from solid ice to liquid water and gaseous steam by a mere rise in temperature, and conversely, by abstraction of heat, steam passes back to water and then to ice. When one's hands get wet, they get cold. A commonplace but convenient proof of this is to wet the finger in the mouth and hold it in the air. A sensible reduction of temperature is instantly noticeable. A more pronounced illustration is to wet the hands in a basin of water and then plunge them in the blast of hot, dry air coming from a furnace register. Instead of warming the hands, as many would suppose, this will, as long as the hands are wet, produce a distinct sensation of increased cold. It is due to rapid evaporation, which in changing the water from a liquid to a gaseous form, abstracts heat from the hands. Evaporation may be effected in two ways. The common one is by applying extraneous heat, as under a tea kettle, in which case the evaporated vapor is hot by virtue of the heat absorbed from the fire. The other way is to reduce pressure or produce a partial vacuum over the liquid without any application of heat, in which case the vapor is made cold. As early as 1755, Dr. Cullen observed this, and discovered that the cold thus produced was sufficient to make ice. An incident of evaporation is the passing from the limited volume of a liquid to the greatly increased volume of a gas. Water, for instance, when it changes to a vapor, increases in volume about 1,700 times. That is, a cubic inch of water makes about a cubic foot of steam. And when evaporation takes place from a reduction of pressure, this involves a dissipation of heat throughout the increased volume, and the corresponding production of cold. When, however, matter changes from a liquid to a gas, or from a solid to a liquid, a peculiar phenomenon manifests itself in that a great amount of heat is absorbed, and, so far as the evidence of the senses goes, disappears in the mere change of state. It is called latent heat. In such case, the heat becomes hidden from the senses by being converted into some other form of intermolecular force not appreciable as a sensible heat, and producing no elevation of temperature. In illustration, if a pound of water at 212 degrees Fahrenheit be mixed with a pound of water at 34 degrees, both being matter in the same state, there results 2 pounds of water at the mean temperature of 123 degrees. If, however, a pound of water at 212 degrees be mixed with a pound of ice at 32 degrees, matter in another state, there will not be 2 pounds of water at the mean temperature of 122 degrees, as might be expected, but 2 pounds at 51 degrees only, an amount of heat sufficient to raise 2 pounds of water 71 degrees, being absorbed in the mere change of ice to water without any sensible raise in temperature. This absorbed heat is called latent heat, and it plays an important part in artificial freezing. A familiar illustration of the absorption of heat in changing from a solid to a liquid is found in the admixture of salt and ice around an ice cream freezer. These two solids, when brought together, liquefy rapidly with an absorption of heat that produces in a limited time a far greater degree of cold than that which could be obtained from the ice by mere conduction, since the reduction of temperature proceeds faster by liquefaction than can be compensated for by the absorption of heat from the air. Were this not true, ice cream could not be frozen by a mixture of salt and ice. Many such freezing mixtures are known, and a few have been made commercially available, but they cannot be economically employed in ice making, and it is therefore only necessary to consider the development of the more common principle of evaporation and expansion, in which the change from a liquid to a gas occurs. The volatile liquid which was first employed was water, but as it did not vaporize as readily as some other liquids, more volatile substitutes were soon found, among which may be named ether, ammonia, liquid carbonic acid, liquid sulfurous acid, bisulfide of carbon, and chymogene, which latter is a petroleum product lighter and more volatile than benzene or gasoline. As these liquids were expensive, it is obvious that their vaporization could not be allowed to take place in the open air, since the reagent would thus be quickly dissipated and lost, and hence means were devised to condense and save this valuable volatile liquid to be used over again. The vaporization of the volatile liquid to produce cold, and its recondensation to liquid form to be used over again in an endless cycle of circulation, seems to have been first effected by Mr. Perkins of England, whose British patent No. 6662 of 1834 affords a simple and clear illustration of the fundamental principles of most modern ice machines. His apparatus is shown in Figure 294. A tank A is filled with water to be frozen or cooled. A refrigerating chamber B, submerged in the water, is charged internally with some volatile liquid, such as ether. When the piston of suction pump C rises, a partial vacuum is formed beneath it, and the volatile liquid in B, being relieved of pressure, evaporates and expands into greater volume, the vapor passing out through pipe F and upwardly opening valve E. This vapor is rendered intensely cold by expansion, and this cold is imparted to the water in tank A to freeze it. A more scientific statement, however, is that the cold vapor absorbs the heat units of the water and, taking them away with it, lowers the temperature of the water to the freezing point. When the piston of pump C descends, valve E closes, and the vapor, laden with the heat units absorbed from the water, is forced through the downwardly opening valve E' and through pipe G to a cooling coil D, around which a body of cold water is continually flowed. This water, in turn, takes the heat units from the vapor and passes off with them in a constant flow, while the vapor of ether is condensed into a liquid again by the cold water, and passing through a weighted valve H, goes into the evaporating or refrigerating chamber to be again vaporized in an endless circuit of flow. It will be seen that the heat units from the water in tank A are first handed over to the cold ether vapors passing out from chamber B, and by this vapor are then transferred to the flowing body of water surrounding the coil D. The result is that the heat units carried off by the water flowing around coil D are the same heat units abstracted from the water in tank A, which water is thus reduced to congelation. Among later ice machines of this type, the Pitot machine was a conspicuous example. This employed anhydrous sulfurous acid as the volatile agent, and is described in United States Patent No. 187,413, February 13, 1877, French patent number 109,003 of 1875. In Figure 295 is represented a vertical longitudinal and also a vertical transverse section of a Pictet ice machine. A is a double-acting suction and compression pump. D and E are two cylinders which are similarly constructed in the respect that they are both provided with flue pipes and heads for a double circulation of fluids, one fluid passing through the pipes, while the other passes through the spaces between the pipes, much like the condenser of a steam engine. The cylinder D is the refrigerator where the volatile liquid is evaporated to produce cold, and the cylinder E is the condenser where the gasified vapor is cooled and condensed again to liquid form to be returned to the refrigerator. The action is as follows. The pump A by pipe B draws from the chamber in the refrigerator D containing the volatile liquid, causing it to evaporate and produce an intense degree of cold which is imparted to the liquid surrounding it and filling the tank. This liquid is either brine, or a mixture of glycerin and water, or a solution of chloride of magnesium, or other liquid which does not freeze, at a temperature considerably below the freezing point of water. Now, this non-congealable liquid being below the freezing point, it will be seen that if cans H be filled with pure water, and are immersed in this intensely cold non-congealable liquid, the water in the cans will freeze. This is exactly what takes place, and this is how the ice is formed. As the volatile liquid is drawn out of the refrigerator D through pipe B by the pump A, it is forced by the pump through pipe C and into the chamber of the condenser E. A current of cold water is kept flowing around the pipes in E, coming in through a pipe at one end and passing out through a pipe at the other end. The compressed and relatively hot gases are by the contact of this cold water along the sides of the pipes cooled and condensed into a liquid again, which passes up the small curved pipe F and is returned to the refrigerator D to be again evaporated by the suction of the pump to continue the production of cold. In large plants, the non-congealable liquid and cans of water to be frozen are, in order to get larger capacity, carried to a large floor tank in a removed situation. One of the earliest methods of producing ice in a limited quantity was by evaporating water by a reduction of pressure and causing the vapor to be absorbed by sulfuric acid, which has a great affinity for the water vapor. Mr. Nairn, in 1777, was the first to discover the affinity that sulfuric acid had for water vapor, and in 1810 Leslie froze water by this means. In 1824, Vallance obtained British patents number 4884 and 5001, operating on this principle, in which leaden balls were coated with sulfuric acid to increase the absorbing surfaces, and which apparatus was effective in freezing considerable quantities of ice. The carafe frappé of the Parisian restaurant were decanters in which water was frozen by being immersed in tanks of seawater, whose temperature was reduced below freezing by the vaporization of ether in a reservoir immersed in the seawater. Edmond Carré's method of preparing carafe frappée involved the use of the sulfuric acid principle of absorption, and to that end the aqueous vapor was directly exhausted from the decanter by a pump, and the said vapor was absorbed by a large volume of sulfuric acid so rapidly as to freeze the water remaining in the decanter. Probably the earliest practical ice machine to be organized on a commercial basis was the ammonia absorption machine of Ferdinand Carré, which was a continuously working machine. It is disclosed in French patents number 81 and 404 of 1860 and number 75,702 of 1867, United States patent number 30,201, October 2, 1860. In this case, advantage is taken first of the very volatile character of anhydrous ammonia in the expansion part of the process, and secondly, of the great affinity which water has for absorbing such gas. Strange as it may appear, the production of ice in the Carré process begins with the application of heat. It must be understood, however, that this forms no part of the refrigerating process proper, but only a means of driving off or distilling the anhydrous ammonia gas, the refrigerant, from its aqueous solution. Ammonia dissolved in water, known as aqua ammonia, is placed in a boiler or still above a furnace. The pure ammonia gas is thus driven off from the water by heat under pressure, similar to that in a steam boiler, and passes direct to a condenser where, by cold water flowing through pipes, the pure gas is liquefied under pressure. The liquefied gas is then admitted to the evaporating or refrigerating chamber, where it expands to produce the cold, and is afterward reabsorbed by the water from which it was originally driven off in the still to be used over again. Machines of this type are known as absorption machines, for the reason that the volatile gas is, after expansion, reabsorbed by the liquid in which it was dissolved, and is continuously driven off therefrom by the heat of a still. Absorption machines were the outgrowth of Faraday's observations in 1823. A bent glass tube was prepared, containing at one end a quantity of chloride of silver, saturated with ammonia and hermetically sealed. When the mixture was heated, the ammonia was driven over to the other end of the tube, immersed in a cold bath, and the ammonia gas became liquefied. It was found by him then that if the end containing the chloride was plunged in a cold bath, and the end containing liquid ammonia was immersed in water, the heat of the water made the ammonia rapidly evaporate, the chloride at the other end of the tube absorbed the ammonia vapors, and the water around the end of the tube containing the liquefied ammonia was converted into ice by the loss of its heat imparted to the ammonia to volatilize it. It only needed the substitution of water for the chloride of silver as an absorbing agent for the ammonia, and mechanical means for economically working the process in a continuous way to produce the Curie absorption machine. The most common form of ice machine today is, however, what is known as the compression or direct system, in which the absorption principle is dispensed with, the ammonia being compressed by powerful steam pumps, then cooled to liquid form by condensers, and then allowed to expand from its own pressure through pipes immersed in brine in a large floor tank, in which cans containing pure water are immersed and the water frozen. Figure 296 shows the compression pumps, and Figure 297 the floor tanks of such a system. Many hundred cans filled with pure water are lowered into the cold brine of the tank, and their upper ends form a complete floor, as seen in Figure 297. When the water in the cans is frozen, the cans are raised out of the floor by a traveling crane and carried to one of the 4 doors seen at the far end of the room. The ice in the can is then loosened by warm water, and the block dumped through the door into a chute, whence it passes into the storage room below, seen in Figure 298. In the can system, the water is frozen from all 4 sides to the center, and imprisons in the center any air bubbles or impurities that may exist in the water. The plate system freezes the water on the exterior walls of hollow plates, which contain within them the freezing medium. In freezing the water externally on these plates, all impurities and air bubbles are repelled and excluded, and the ice rendered clear and transparent. An ice plant, employing what is known as the can system, and capable of producing 100 tons of ice in 24 hours, requires a building about 100 feet wide and 150 feet long on account of the great floor space needed to accommodate the freezing tank and the great number of cans which are immersed in the same. A radical departure from this style of plant is presented in the Holden ice machine. This does not require a multitude of cans and a great floor space, but a lot 25 by 50 feet is sufficient, for the ice is turned out in a continuous process like bricks from a brick machine. The machine works on the ammonia absorption principle, but the freezing is done on the outer periphery of a revolving cylinder, from which the film of ice is scraped off automatically, and the ice slush carried away by a spiral conveyor to one of 2 press molds, in which a heavy pressure solidifies the ice into blocks, which are successfully shot down from the presses on a chute to the storage room, as seen in Figure 299. The foregoing examples of ice machines give no idea of the great activity in this field of refrigeration in the 19th century. Over 600 United States patents have been granted for ice machines alone, to say nothing of refrigerating buildings, refrigerator cars, domestic refrigerators, and ice cream freezers, etc. Among the earlier workers in ice machines, in addition to those already named, may be mentioned the names of Gorey, patent number 8080, May 6, 1851, followed by twining, 1853 to 1862, Mignon and Ruard in 1865, Lowe in 1867, Soames in 1867 to 1868, Windhausen in 1870, Rankine in 1876 to 1877, and many others. An application of the ice machine which attracted much attention and attained great popularity for a while was that made in the production of artificial skating rinks, in which a floor of ice was frozen by means of a system of submerged pipes, through which the cold liquid from the ice machine was made to circulate. The earliest artificial skating rink is to be found in the British patent to Newton, No. 236 of 1870, but it was Gamgee, in 1875 and 1876, who devised practical means for carrying it out and brought it into public use. His inventions are described in his British patents No. 4412 of 1875 and No. 4176 of 1876, and United States Patent No. 196,653, October 30th, 1877, and others in 1878. The Windhausen machine was one of the earliest applications for cooling and ventilating ships. This machine operated upon the principle of alternately compressing and expanding air, and is described in United States Patents No. 101,198, March 22, 1870, reissue No. 4603, October 17, 1871, and No. 111,292, January 24, 1871. Today, every ocean liner is equipped with its own cold storage and ice-making plant. Refrigerator cars transport vast cargoes of meats, fish, etc. across the continent, and bring the ripe fruits of California to the eastern coast. Every market house has its cold storage compartments, and to the brewery, the refrigerating plant is one of its fundamental and important requisites. The great value of refrigerating appliances is to be found in the retardation of chemical decomposition or arrest of decay, and as this has relation chiefly to preserving the foodstuffs of the world, its value can be easily understood. This branch of industry has grown up entirely in the 19th century, and the activity in this field is attested by the 4,000 United States patents in this class. End of Chapter 32.
Chapter 35 of the Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Progress of Invention in the 19th Century by Edward Wright Byrn. Liquid air. Until quite recently, the physicist divided gaseous matter into condensable vapors and permanent vapors. Today it is known that there are no permanent gases, since all the so-called permanent gases, even to the most tenuous, such as hydrogen, may be made to assume the liquid and even the solid form. The average individual knows very little about hydrogen, but he is very well acquainted with air. And when he was told that the air that he breathes, the gentle zephyr that blows, the wind that storms from the north, or twists itself into the rage of a cyclone in Kansas, may be bound down in liquid form and imprisoned within the limits of an open-air tumbler, or be bottled up in a flask or even frozen solid, he was at first impressed with the suspicion of a fairy story. Seeing is believing, however, to him, and the striking experiments from the lecture platform, the approval of the scientists, and the sensational accounts of it in the press, have not only been convincing, but have completely turned his head and made him a too willing victim of the speculator. Liquid air is a real achievement, however, and while it is astonishing to the layman, the physicist looks upon it in the most matter-of-fact way, for it is only a fulfillment of the simplest of nature's laws, and entirely consonant with what he has been led to expect for many years. The liquefaction of gases has engaged the attention of the scientist almost from the beginning of the century. In 1805-6, Northmore liquefied chlorine gas This was done again in 1823 by Faraday. In 1824, Bussy condensed sulfurous acid vapors to liquid form. In 1834, Phil-Ourier made extensive experiments and demonstrations in the liquefaction of carbonic acid gas. In 1843, Ames experimented with the liquefaction of gases by sinking them in suitable vessels to great depths in the ocean. Natterer, in 1844, greatly advanced the study of this subject by both novel methods and apparatus. Liquefaction of air was attempted as early as 1823 by Perkins, and again in 1828 by Colladon, but it was not accomplished until 1877. In this year, the liquefaction of oxygen, the Pictet of Geneva and Calitet of Châtillon-sur-Seine, was independently accomplished. Pictet used a pressure of 320 atmospheres and a temperature of negative 140 degrees, obtained by the evaporation of liquid sulfurous acid and liquid carbonic acid. Calitet used a pressure of 300 atmospheres and a temperature of negative 29 degrees, which latter was obtained by the evaporation of liquid sulfurous acid. In 1883, Dewar, Wroblewski, and Zalewski commenced operations in this field and greatly advanced the study of this subject. In January of 1884, Wroblewski confirmed the liquefaction of hydrogen, which had been imperfectly accomplished by Calitet before. In the liquefaction of oxygen and nitrogen, the principal component gases of air, the liquefaction of air itself followed immediately as a matter of course. Air has usually been held to consist of 4 volumes of nitrogen and 1 volume of oxygen, with a very small proportion of carbonic acid gas and ammonia. Recent discoveries have definitely identified new gases in it, however, chief among which is argon. For all practical purposes, however, air may be considered simply a mixture of the 2 gases, nitrogen, which is inert and neither maintains life nor combustion, and oxygen, which performs both of these functions in a most energetic way. Air is more dense at the surface of the earth and becomes continually more rarefied as the altitude increases, until it becomes an indefinitely tenuous ether. Light as we are accustomed to regard it, the weight of a column of air, 1 inch square, is 15 pounds, and this tenuous and unfelt covering presses upon our globe with a total weight of 300,000 million tons. Liquid air is simply air which has been compressed and cooled to what is called its critical temperature and pressure. For example, the temperature and pressure at which it passes into another state of matter, as from a gas to a liquid. To liquefy air, it is compressed until its volume is reduced to 1/800th. That is to say, 800 cubic feet of air are reduced to 1 cubic foot. This requires a pressure of 1,250 to 2,000 pounds to the square inch. The important step in liquefying air cheaply and on a large scale was accomplished by the discovery of what is known as the self-intensifying action. This dispenses with auxiliary refrigerants and causes the expanding gases to supply the cold air required for their own liquefaction by an entirely mechanical process. It consists in compressing the air, which produces heat, then cooling it by a flowing body of water, then passing it through a long coil of pipes and expanding the cool compressed air by allowing it to escape through a valve into an expansion chamber, where its pressure falls from 1,250 pounds to 300 pounds, which produces a great degree of cold, then taking this very cold current of air back in reverse direction along the walls of the coil of pipes, and causing said returning cold air to further cool the air flowing from the compressor to the expansion tank, and finally delivering the cold return flow to the compressors and compressing it again from a lower initial point than it started with on the first round, and so continuing this cycle of circulation through the alternating compressing and cooling stages until the air condenses in liquid form in the bottom of the expansion chamber. This successive reduction of temperature by the air acting upon itself is called self-intensification of cold, and it has an analogy in the regenerative furnace, or the augmentation of heat corresponds to the augmentation of cold in the self-intensifying action. This principle of self-intensification was first announced by Professor C. W. Siemens in the provisional specification of his British patent number 2064 of 1857, but it does not seem at the time to have been carried out with any practical result. The first embodiment of the principle in a refrigerating apparatus is by Windhausen, United States Patent number 101,198, March 22, 1870. Solvay in British Patent number 13,466 of 1885 gave further development to the idea, and came the operations of Professor Tripler, who was the first to liquefy large quantities of air and to introduce it to the American people. Lind Hampson and Ostergren and Berger are more recent operators in this field of self-intensification, and Lind's British Patent number 12,528 of 1895 may be regarded as a representative exposition of the principle. A simplified form of the Lind apparatus is seen in Figure 300. C is an air-compressing pump whose plunger descending compresses the air and forces it out through valve 1, pipe 2, and coil 3. The coil 3 is immersed in a flowing body of water in the condenser W, the water entering at Y and passing out at Z. The cold compressed air then passes through pipes 4 and 5, pipe 5 being arranged concentrically within a larger coil 7. The cold air flowing down pipe 5 escapes through a valve adjusted by handle 6 into the subjacent chamber L, and expanding to a larger volume produces a great degree of cold. This cold expanded air, then passing up the larger and outer pipe 7, flows back over the incoming stream of air in pipe 5, chilling it still lower than the condenser W did. And this cold return flow, then passing from the top of coil 7, descends through pipe 8 to the compressing pump C, and as its piston rises, it enters the pump through the inwardly opening valve 9, and here it undergoes another compression and circuit through the pipes 2, 3, 4, 5, but it is compressed on its second round of travel at a lower temperature than it had initially, and so this circulation of air going to the chamber L, expanding and returning over the inlet flow pipe 5, successively cooling the latter and also successively entering the compressor at a continually lower temperature at each cycle of circulation, finally issues through the valve at the lower end of pipe 5 and expands to such a low temperature that it condenses in chamber L in liquid form. Fresh accessions of air are furnished to the apparatus through valve 10 as fast as the air is liquefied. The inlet flow to the liquefying chamber is shown by the full line arrows and the return flow to the compressor by the dotted arrows, and the explanation of the term self-intensification is to be found in the cooling of the incoming air in pipe 5 by the outflowing air in the surrounding pipe 7, and the repeated reductions of temperature at which the air is returned to the compressor. In Figure 301 is shown the liquefier of a modern liquid air plant, in which liquid air is being drawn into a pail from the liquefier. Liquid air evaporates very rapidly and produces the intense cold of 312 degrees below zero. There is no known way to preserve it beyond a limited time, for if put in strong, tightly closed vessels, it would soon absorb enough heat to vaporize, and in time would acquire a tension of 12,000 pounds per square inch. It would burst the vessel with a disastrous explosion, if left exposed to the air, which is the only safe way to transport it. It is quickly dissipated. A shipment of 8 gallons from New York to Washington for lecture purposes shrunk to 3 gallons in 2 days' time. It may usually be kept longer than this, however, as the jarring of a railway train promotes its evaporation and loss. A small quantity, which, as a half pint, will boil away in 25 to 30 minutes. The only way to preserve it for any length of time is to surround it with a heat-excluding jacket. The simplest and most effective means for doing this in the laboratory is to surround it with a vacuum. Figure 302 shows a specially devised vessel for the commercial transportation of liquid air. A double-walled globular vessel has between its walls air spaces and non-conducting packing. The liquid air in the interior chamber vaporizes gradually, and escaping through the outwardly opening valve at the top, expands around the air space surrounding the inner vessel. From this space it reaches the outer air by a valve at the bottom of the outer vessel. The liquid air in evaporating is thus carried around the body of liquid air in the center, and surrounding it with an intensely cold envelope prevents the transmission of heat to the inner vessel. To withdraw the liquid air, a pipette or so-called siphon tube, shown in detached view, is substituted for the valve at the top. As to the uses of liquid air, it may be said that up to the present time, it has attained little or no practical application. There are two principal ways in which it may be utilized. One is to employ its enormous expansive force to produce mechanical power, and the other is as a refrigerant. As a means for obtaining motive power, it is a fallacy to suppose that any more power can be obtained from its expansion than was originally required to make it. It is like a resilient spring in this respect, that it can give out no more power than was required to compress it. In some special applications, however, as for propelling torpedoes, where its cost is entirely subordinate to effective results, it might prove to be of value. For blasting purposes also it presents the promise of possible utilization as a refrigerant for commercial purposes, and for supplying a dry, cool temperature to the sick room, and for the preparation of chemicals requiring a low temperature to manufacture. It might find useful application. Inasmuch as the nitrogen of liquid air evaporates first and leaves nearly pure liquid oxygen, it may also be employed as a means for producing and applying oxygen. Good illustration of this is given in Figure 303, in which at 1 is shown a vessel filled with liquid air. The gas first evaporating is nitrogen, and a lighted match applied to the surface of the liquid is quickly extinguished, since nitrogen does not support combustion. As the level of the liquid falls by evaporation, the remaining portions become richer in oxygen and poorer in nitrogen. A nitrous oxide gas is then given off, which supports combustion as seen at 2, and when the last portions of the liquid are being evaporated, as at 3, it is practically pure oxygen, which gives a brilliant combustion of a carbon pencil, or even of a steel spring, when the latter is heated at red hot. Already, Professor Piotr has formulated a plan for the commercial production and separation of the ingredients of liquid air and nitrogen, carbonic acid, and oxygen being separated by their different evaporating temperatures with a view to applying them to various industrial uses. All of the commercial applications of liquid air, however, depend upon its cost of production, which seems at present an uncertain factor. According to the claims of some, it may be produced at a cost of a few cents a gallon. More conservative physicists say that it costs $5 a gallon. However, this may be the phenomena which it presents are both interesting and instructive. In Figures 304 and 305 are shown some of the experiments. At number 1, a test tube containing liquid air from which the nitrogen has escaped is strongly attracted by an electromagnet, showing the magnetic quality of oxygen. At number 2 is shown the combustion of a heated piece of steel in liquid air, which has become rich in oxygen by the evaporation of the nitrogen. At number 3, a tin dipper, which has been immersed in liquid air, has become so cold and crystalline that it breaks like glass when dropped. At number 4, liquid air imprisoned in a tube, corked up, blows the stopper out in a few minutes with explosive effect. At number 5, a piece of paper saturated with liquid air burns with great energy. And at number 6, a piece of sponge or raw cotton, similarly saturated, explodes when ignited. At number 7, a rubber ball floated on liquid air in a tumbler is frozen so hard that when dropped it flies into fragments like a glass ball. The white, snow-like vapor seen falling over the edges of the tumbler is intensely cold and heavier than ordinary air. At number 8 is illustrated the preservation of liquid air by surrounding it with a vacuum in a Dewar bulb. At number 9, a flask of liquid air is made to boil by the mere heat of the hand. A more striking experiment, still of the same kind, is to place a tea kettle containing liquid air on a block of ice. The block of ice is relatively so much hotter than the liquid air that the liquid air in the kettle is made to boil. At number 10, figure 305, a heavy weight is suspended by a link composed of a bar of mercury frozen solid in liquid air. So hard is the mercury frozen that a hammer made of it will drive a 10-penny nail up to its head in a pine board. In number 11, a layer of liquid air on water at first floats, because it is lighter than water. As the lighter nitrogen evaporates, the heavier oxygen sinks and drops through the water. At number 12, a tumbler of whiskey is frozen solid by immersing a tube containing liquid air in it. The frozen block of whiskey with the cavity formed by the tube is shown on the left. It is a whiskey tumbler made out of whiskey. A more sensational experiment is to substitute a tapering tin cup for the tube, then fill it with liquid air and immerse it in water. In a few minutes, the tapering tin cup has frozen on its outer walls a tumbler of ice. This may be carefully removed, and the ice tumbler is then filled with liquid air rich in oxygen, which, by maintaining the cold of the ice tumbler, keeps it from melting. A carbon pencil or a steel spring heated to redness will now, if dipped in the liquid oxygen in the ice tumbler, burn with vehement brilliancy and beautiful scintillations, involving the anomalous conditions of a white-hot heat and active combustion in the center of a tumbler of ice without melting the tumbler. In experiment 13, figure 305, a jet of carbonic acid gas directed into a dish floating in a glass of liquid air is immediately frozen into minute flakes, producing a miniature snowstorm of carbonic acid. In experiment 14, an electric light carbon heated to a red heat at its tip is plunged vertically into a deep glass of liquid oxygen. A most singular combustion takes place. The heat of the carbon evaporates the oxygen in its immediate vicinity, and the carbon burns with great brilliancy and violence, forming carbonic acid, which is largely frozen in the liquid before it reaches the surface, and falls back to the bottom of the dish, so that the combustion is maintained and its products retained within the dish. A beefsteak may be frozen in liquid air to such brittleness that it is shattered like a china plate when struck a slight blow. The intense cold of liquid air does not destroy the vitality or germinating power of seed, but produces serious so-called burns on the flesh that destroy the tissues and do not heal for many months. And yet for a moment the finger may be dipped in liquid air with impunity because of the gaseous envelope with which the finger is temporarily surrounded. End of chapter 35. Chapter 36 of The Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Progress of Invention in the 19th Century by Edward Wright Byrn. Chapter 36, Minor Inventions and Patents of Principal Countries of the World. If the reader has been patient enough to have reviewed the preceding pages, the impression may have been formed that the notable inventions referred to represent all that is worth while to consider in this great field of human achievement. It would be a fallacy to entertain such a thought, for the little stars outnumbered the big ones, and the twigs of the tree are far more numerous than its branches. The great things in life are comparatively few and far between, and the bulk of human existence is made up of an unclassified mass of little things, sown like sands along the shore of time, between the boulders of great events. So also in invention is its warp and woof, made up of a multitude of little threads behind the gorgeous patterns of meteoric genius. Every hour of the day of modern life is replete with the achievements of invention. Look around the room, and there is not a thing in sight that does not suggest the material advance of the age. The books, the furniture, the carpets, the curtains, the wallpaper, the clock, the mantels, the house trimmings, the culinary utensils, and the clothing, all represent creations of this century. So full is the daily life of these things, and so much of a necessity have they all become, that their commonplace character dismisses them from conspicuous notice. Take the most matter-of-fact and prosy half-hour of the day, that at the time of rising, and see what a faithful account of the average man's everyday life would present. The awakening is definitely determined by an alarm clock, and the sleepy 19th century man, rolling over under the seductive comfort of a spring bed, takes another nap, because he knows that the rapid transit cars will give him time to spare. Rising a little later, his bare feet find a comfortable footing on a machine-made rug, until thrust into full-fashioned hose, and ensconced in a pair of machine-sewed slippers. Drawing the loom-made lace curtains, he starts up the window shade on the automatic hartshorn roller, and is enabled to see how to put in his collar button and adjust his shirt studs. He awakens the servant below with an electric bell, calls down the speaking tube to order breakfast, and perhaps lights the gas for her by the push button. He then proceeds to the bath, where hot and cold water, the sanitary closet, a gas heater, and a great array of useful modern articles present themselves, such as Vaseline, witch hazel, dentifrices, cold cream, soaps, and antiseptics, which supply every luxurious want and every modern conception of sanitation. His bath concluded, he proceeds to dress, and maybe puts in his false teeth or straps on an artificial leg. Donning his shirt with patented gussets and bands, he quickly adjusts his separable cuff buttons, puts on his patented suspenders, and, winding a stem-winding watch, proceeds downstairs to breakfast. A revolving fly brush and fly screen contribute to his comfort. A cup of coffee from a drip coffee pot. A lump of artificial ice in his tumbler. Sausage ground in a machine. Batter cakes made with an egg beater. Waffles from a patented waffle iron. Honey in an artificial honeycomb. Cream raised by a centrifugal skimmer. Butter made in a patented churn. Hot biscuits from the cooking range. And a refrigerator with a well-stocked larder. All help to make him comfortable and happy. The picture is not exceptional in its fullness of invented agencies, and one could just as well go on with our citizen through the rest of the day's experience, and start him off after breakfast with a patented match, in a patented match case, and a patented cigarette, with his patented overshoes and umbrella, and send him along over the patented pavement to the patented streetcar or automobile, and so on to the end of the day. Some of the minor inventions are really of too much importance to be passed without comment. The cable car is a factor which has cut no small figure in the activities of city life. The first patent on a slotted underground conduit between the rails, with traction cable inside and running on pulleys, was that to E. A. Gardner, number 19,736, March 23, 1858. Halliday, in San Francisco, in 1876, directed his energies to a development of this system, and brought it to a degree of perfection and general adoption that made it for many years the leading system of streetcar propulsion. Today, however, it represents but a decadent type, being largely supplanted by the superior advantages of electricity. Passenger elevators constitute one of the conspicuous features of modern locomotion. Without them, the tall office buildings, hotels, and department stores would have no existence. The Eiffel Tower would never have been dreamed of, and the expenditure of vital force in stair climbing would have been greatly augmented. The passenger elevator has for its prototype the ancient hoist or lift for mines, but in the latter half of the 19th century it has developed into a distinct institution, a luxurious little room, gliding noiselessly up and down, actuated by a power that is not seen, and supplied with every appliance for safety and comfort, such as governors, safety catches, automatic stops, mirrors and cushioned seats, the principle of the screw, of balance weights, of the lazy tongs, and other mechanical powers have each found application in the elevator. but steam, hydraulic power, and electricity constitute the moving agencies of the modern type. The patent to E.G. Otis, number 31128, January 15, 1861, marks the beginning of its useful applications. Of close kin to the elevator are the fire escape, dumbwaiter, and grain elevator, each of which fills a more or less important function in the life of today. What more ubiquitous or ingenious illustration of modern progress than the American stem winding watch? Up to the middle of the century, all watches were made by hand throughout. Each watch had its own individuality as a separate creation, and only the privileged few were able to carry them. In 1848, Aaron L. Dennison, a Boston watchmaker, began making watches by machinery, and the foundation of the system of interchangeable parts was laid. A small factory at Roxbury, Massachusetts, was established in 1850, which 4 years later was moved to Waltham. In 1857 it passed into the hands of Appleton, Tracy and Company, and was subsequently acquired by the American Watch Company, as presenting some idea of the great elaboration involved in this art. It was estimated a few years ago that 3,746 distinct mechanical operations were required to make an ordinary machine-made watch. A single pound of steel wire is sometimes converted into a couple of 100,000 tiny screws, and another pound of fine steel wire furnishes 17,280 hair springs, worth several $1,000s. The absolute uniformity and perfect interchangeability of parts in the American watch have been obtained by substituting the invariable and mathematical accuracy of the machine for the nervous fingers and dimming eyes of the old-time watchmaker. And the American machine-made watch, discredited as it was at first, stands today the greatest modern advance in horology. Friction matches in 1805, Thenard of Paris made the first attempt to utilize chemical agencies for the ordinary production of fire. In 1827, John Walker, an English druggist, made friction matches called Congraves. In 1833, phosphorus friction matches were introduced on a commercial scale by Preschel of Vienna. In 1845, red phosphorus matches, parlor matches, were made by von Schroeder of Vienna. And in 1855, safety matches, which ignited only on certain substances, were made by Lundstrom of Sweden. Prior to the 19th century, and in fact until about 1833, the old flint and steel and tinderbox were the clumsy and uncertain means for producing fire. Today the friction match is turned out by automatic machinery, by the million, and constitutes probably the most ubiquitous and useful of all the minor inventions. Step into any of the great department stores, and the genius of the inventor confronts you in the cash carrier whisking its little cars back and forth from the cashier's desk to the most remote corners of the great building. The first of these mechanical carriers adapted for store service was patented by D. Brown, July 13, 1875, number 165,473. Not until about 1882, however, was there any noticeable adoption of the system, when practical development was given in Martin's patents, number 255,525, March 28, 1882, number 276,441, April 24, 1883, and number 284,456, September 4, 1883. Go to the lunch counter, and the cash register reminds you that the millennium of absolute honesty is not yet realized. The bell punch on the streetcar and the burglar-proof safe with its combination locks are other suggestions in the same line. The first fireproof safe is disclosed in the British patent to Richard Scott, number 2477, of 1801. The time lock, which prevents the safe from being opened by anyone except at a certain period of daylight, was invented by J. V. Savage, and was covered by him in United States Patent number 5321, October 9, 1847. The practical adoption of time locks began about 1875, with the operations of Sergeant Stockwell and others, and today They constitute one of the most important features of bank safes and vaults, and represent a marvelously beautiful and accurate example of mechanical skill. The auto gas engine and the Ericsson air engine are important developments in power-producing motors, and the improvements in pavements and in street sweepers for cleaning them contribute to the cleanliness, sanitation, and aesthetic values of city life. The cigarette machine, which continuously curls a ribbon of paper around a core of tobacco to form a rope, and then cuts it off into cigarettes, is an important invention in the tobacco industry, however doubtful its hygienic value to the world may be. The lightning rod has brought protection to homes and lives, and the incubator has become the hen's wet nurse. In agriculture, the reaper has been supplemented with threshing machines, seeders, drills, cultivators, horse rakes, and plows. In the farmyard appear the improved carriage and wagon, the well pump, the wind wheel, the fruit dryer, the beehive, and the cotton and cider press. In the kitchen, the washing machine, the churn, the cheese press, ironing machine, wringer, the rat trap, and fruit jar. In the house, the folding bed, tilting chair, carpet sweeper, and the piano. In heating appliances, steam and water heating systems, base burning and Latrobe stoves, hot air furnaces, gas and oil stoves. In plastics, there are brick machines, pressed glassware, enameled sheet ironware, tiles, paper buckets, celluloid, and rubber articles. In hydraulics, there are rams, water closets, pumps, and turbine water wheels. In mining, there are stamp mills, ore crushers, separators, concentrators, and amalgamators. In the leather and boot and shoe industry, there is a great variety of machines and appliances. The paper industry, with book-binding machines and paper box machines, is a fertile field of invention. Steam boilers, metallurgical appliances, soap making, chemical fire extinguishers, fountain pens, the sand blast, bottle stoppers, and 1,000 other things present themselves in miscellaneous and endless array. These are, however, only some of the things which the limitation of space precludes from individual treatment, but which are none the less important in making up the great resources of modern life, and for the most part represent the contributions of the 19th century, not heretofore considered. The observant and thoughtful reader finds just here occasion to inquire the meaning of this great rising tide of progress, which has so distinguished the 19th century. It is largely due to the patent law, which justly regards the inventor as a public benefactor, and seeks to make for him some protection in the enjoyment of his rights. If a man be in the possession of a legacy by the accident of birth, the law of inheritance rules that it is rightfully his. The finding of a thing, whether by jetsam, flotsam, or the lucky accident of a first discovery. This also makes good his title, if there be no other owner. There is, however, a right of property which is higher than all others, and in which there is coupled with the possession of the thing the sacred function of its creation. The right of a mother to her child is of this nature, and like unto it is the right of the inventor to the creation of his genius. In the last 2 centuries of the world's history, this right has been recognized by an enlightened civilization, and provision made for its enjoyment in the grant of patents. And if there be any right more strongly entrenched than another in the eternal verities of equity and justice, it is this. Our first crude patent law was enacted in 1790, but not until 1836 was the present system adopted. Our own and comparatively new country has, therefore, not yet had 100 years of existence under our present patent system, and yet today it outstrips the world both in its material resources and in its wealth of patented inventions. The accompanying diagram, figure 306, illustrates in a graphic way just what relation the United States bears to the other leading countries of the world in the matter of patents granted. And when it is remembered that under our system a patent can only be granted for a new invention, while in some of the other countries it is not essential to the grant, The richness in invention of the United States, with its 650,000 patents, can be better appreciated. This is a greater number than has been issued by Great Britain and France put together. Connecticut is the most productive state in invention in proportion to its people, and Edison is the most prolific inventor. From 1870 to 1900, he has taken 727 United States patents, and there are from 25 to 30 other American inventors, each of whom has taken 100 or more patents. The year 1790 was notable in two events: the birth of our patent system and the death of Benjamin Franklin. That grand old philosopher, with a prescience of future greatness to come from the genius of the inventor, is said to have expressed the wish before he died that he might be sealed up in a cask of old Madeira and be brought to life 100 years in the future, that he might witness the growth of the world. Who can tell what his emotions would be if he were with us today? It is said when he first saw the fibers of the string diverge, and the spark pass from the cord of his kite, and the lightning was for the first time obedient to the will of man, that he uttered a deep sigh, and wished that that moment were his last. To his poor knowledge of electricity he would now have added all the wonders and powers of the telegraph, the dynamo, the telephone, and the great modern electrical science. To his primitive hand press he would have contrasted the octuple perfecting press, turning out papers at the rate of 1,600 a minute. His modest typesetting case would be replaced by a great array of linotype machines, and he would find several acres of woodland sacrificed to produce the wood pulp paper of a single edition of a New York daily. Would he not realize indeed that truth is stranger than fiction, in fact more wonderful than fancy's dream? End of section 36.
Chapter 35 of The Progress of Invention in the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Verla Viera. The Progress of Invention in the 19th Century by Edward Wright Byrn. Epilogue. Whatever the future centuries may bring in new and useful inventions, certain it is that the 19th century stands preeminent in this field of human achievement, so far excelling all other like periods as to establish on the pages of history an epoch as remarkable as it is unique. Never before has human conception so expressed itself in materialized embodiment. Never has thought been so fruitfully wedded to the pregnant possibilities of matter. Never has the divine function of creation been so closely approximated. Never has such an accretion of helpful instrumentalities and material resources been added to the world's wealth, not merely the miserly and inert wealth of gold and gems, but the wealth of an enlarged human existence. This life itself is but a limited span beginning in infancy, expanding to highest achievement in middle age, and declining at the end. It quickly passes away, and another generation follows. Growth and decay with all living things mark the immutable law of nature, and the inevitable fate of mortality. The rose blossoms into beauty, fades, and decays. The bird in the air and the beast in the field each plays his part and passes to the great unknown, leaving no record. Man himself is mortal, but his work is immortal. The inspired conception of his best thought, the materialized embodiment of his work in useful agencies, and the subjugation of the laws of nature to his service, all endure and live forever in his inventions. These partake of the breath of life, and in their immortality are of kin to the soul. Cities may grow up and vanish, civilizations may decay, and man himself may degenerate, but the principle of the lever and the screw, once discovered, is for all time perfect, invariable, and immortal. Every invention made is another permanent gift to posterity. All of enduring wealth that the present gets from the past are its ideas reduced to a working basis. All else is but dross, or evanescent dreams which vanish into oblivion in the light of a larger knowledge. But ideas wrought into practical, substantive things, tried and proven true, these are inventions, immortal creations, and of these the 19th century has borne fruit in paramount abundance, and this legacy it now bequeaths to the coming century. To follow conventional methods, the final chapter of a book should be an in conclusion with a finis and a dismantled torch, but the history of invention will ever be a continued story. There is no end in this field. The trusteeship of the 20th century man is great, and great his responsibilities, but his restless and dominant spirit knows no decadence, and his mental endowment and material equipment, without parallel in history, are a guarantee of future achievements. Will not the chemist learn how to produce electricity direct from the combustion of coal, or solve the problem of the synthesis of food? Will not the American continent be parted by an interoceanic channel, or the rough waters of the English Channel be avoided with a submarine tunnel? May not a ship canal through France to the Mediterranean give to that country the connected enjoyment of riparian rights without passing the frowning battlements of Gibraltar? Or might not a tunnel under the Straits of Gibraltar put Europe and Africa in direct railway communication? The relation of electricity to life is a field of pregnant possibilities, and may we not also learn to swap the surplus heat of summer for the winter's cold, and by an equalization of their two extremes bring eternal spring and joy to the animated world? Shall we not yet stand on the North Pole, or looking away into space, may we not extend a neighborly welcome to our brothers in Mars, if any there be? It is permitted to dream in this field, for it is this reaching out into the unknown that plats the boundaries of an extended world and adds to the possessions of man. The old man, in his dreams of the past, rejoices in his achievements, for he has stolen the fires of Prometheus and forged anew the thunderbolts of Jove for the arts of peace. Delving into the secret recesses of the earth, he has tapped the hidden supplies of nature's fuel, has invaded her treasure house of gold and silver, robbed Mother Earth of her hoarded stores, and possessed himself of her family record, finding on the pages of geology 60 millions of years' existence. Peering into the invisible little world, the infinite secrets of microcosm have yielded their fruitful and potent knowledge of bacteria and cell growth. Pain has been robbed of its terrors by anesthesia. The heat of the sun has been brought down in the electric furnace, and the cold of interstellar space in the ice machine and liquid air. With telescope and spectroscope, he has climbed into limitless space above, and to find the size, distance, and constitution of a star millions of miles away. The North Star has been made his sentinel on the sea. The lightning is made his swift messenger, and thought flashes in submarine depths around the world. Dead matter is made to speak in the phonograph. The invisible has been revealed in the X-rays. Coal has been made his black slave, steam the breath of the world's life, and all of nature's forces have been made his constant servants in attendance. With such a retrospect, the sage of the 19th century may lie down to quiet rest, with an assuring faith that what God hath wrought is good, and what is not may yet be. End of Epilogue. End of the Progress of Invention in the 19th Century by Edward Wright Byrn.